All right, let's get started. Welcome to the final day of this Evado bootcamp on agents. I hope you've really enjoyed and you've been excited by the many new ideas throughout this bootcamp. Today's session will be on multi-agent interactions and human-in-the-loop interaction. We have a great series of speakers today, so I'll try to not take up too much of their time. I'll introduce our first speaker, Alane. So Alane is a assistant professor at ECS and Bear at UC Berkeley. Her work focuses on building language using systems that communicate with and learn from human users in collaborative, situated interactions. Prior to joining Berkeley, Alane completed a PhD in computer science at Cornell University, Cornell Tech, and spent a year afterwards as a young investigator at the Allen Institute for AI. Please give a round of applause for Alane. Thank you.
Okay, yeah, so I wanted to start off the day by talking about sort of a whirlwind tour of different things going on in multi-agent systems. So I'm going to cover like 4 different questions today. First, what does it mean to be multi-agent, and why is this like a hard problem in ways that we might not have seen before in the previous 3 days? Second, how can we actually evaluate and deploy multi-agent systems? What are the kinds of tasks that they're doing, that sort of thing? How do we actually build agents that participate in multi-agent interactions? And then finally, how are we actually using these in practice? Like, what are their uses in the real world? Why are people interested in this problem? Okay, so we've talked a lot about agents in the last couple of days. One definition is like an entity that intervenes on the sort of state of the environment or like dynamic system in which it is embodied by taking actions. So for example, we talked 2 days ago about like computer use agents. And these are agents that take observations. So for example, like the current screenshot state of a UI, and goals, which might be defined through natural language. So something like, clear the trash bin out of my, desktop or something like that. And then the agent maps from that observation and that goal to a series of actions. So in the computer use setting, it's moving around the cursor, it's clicking things, it's typing things, that sort of thing. Another example, potentially in like the robotics domain, like we talked about yesterday, is a navigation agent that takes sort of a natural language description of a trajectory. Like I think we had the instructions like find something that I could wear to a space-themed party. And its current observations of the world surrounding it, and then takes actions in the form of navigation actions to achieve that goal. So these are single agent systems that intervene on the surrounding environment by taking actions like navigation or clicking, typing, that sort of thing. In a multi-agent system, we have an environment, but we have multiple agents that are performing interventions on the state of the environment at the same time. These agents might have different goals, and the main thing here is that other agents' actions might impact the environment state in unfamiliar ways that, as a single agent system are hard to model because you have another agent in the world that is also influencing the environment in pursuit of its own independent goals. So for example, this is an example from a multi-agent environment from DeepMind called Melting Pot. This is like the cleanup game in Melting Pot. The environment itself, its dynamics include the fact that like apples, which are at the red things at the bottom, grow in an orchard, so they randomly appear at a certain rate. And the rate at which those apples appear is influenced by the cleanliness of the river. So you can see that sometimes the river gets these little green spots in the top. That slows down the rate of apple growth. As an individual agent, if you were the only agent in this environment, your reward would be pick as many apples as possible. And you have this sort of tension between having to like clean up the river or pick the apples. Now that you have multiple agents in this environment, you could actually distribute this work, right? You could have some agents clean the river, some agents pick the apples. There's also this factor where you could have agents that could zap other agents from the game, for example, if they are taking up all the apples and not helping with cleaning up the river. So different ways that we could incentivize the agents or reward them in this game influences their behavior. So for example, if all the agents are working together to individually achieve their maximum reward, they might coordinate with each other. The best strategy might be to coordinate with each other by taking turns. So having some agents clean up the river while others are doing the apples and then switching every so often. If, for example, some of the agents in the environment are free riders, meaning that they're only taking apples, then maybe there's an alternative strategy that's optimal. For example, the agents that are not free riders might clean the river as quickly as possible such that the rate of apple growth is outpacing the rate of the free riders like eating the apples. So here's just a little taste of how like the interaction incentives and interaction design is influencing the sort of multi-agent strategies that come up here, right? And the fact that there are multiple agents that could make the goals harder or easier is influencing that behavior. So why is multi-agent modeling hard? So in a single agent setting, the state of the environment is influenced only by the actions that that agent is taking. So we have T here is the transition function. This is a function that tells us if you have some state S and some action A, what is the distribution over possible next states? The notation here is like delta with the S at the top. And so this is a function that tells us, if you take action in state S, then you will see some distribution of states. And there's some stochasticity here because there might be some like underlying just noise in the environment, right? That's not necessarily caused by other agents. And this, for example, allows agents to estimate what the optimal multi-step trajectory would be towards a goal. Because we can sort of do some inverse planning to identify what is the state that we want to get and what are the actions that would most likely get us there. But in multi-agent modeling, the state is not just influenced by the action of me, the agent. It's also influenced by the actions of other agents in the environment. So if we have like n agents, we have A1, A2, A3, all the way up to AN actions that could influence the current state, the next state of the environment. And so unless I have perfect knowledge of how the other agents are taking actions, this makes the problem pretty hard. Because if I want to study, if I want to model how the environment is changing, it is in my best interest to also model how the other agents are going to act. So then I need to model what other agents are doing. So if we say that an agent is notated by pi, and we have pi I, which is like the ith agent in the environment, then I could say my estimate, what I'm trying to do is estimate how that other agent is going to behave. So that other agent is taking some observations of the world, O, and some goal, G, and it's going to produce a distribution over possible next actions. And I, as my own agent, want to estimate this for all the other agents in the environment. So this includes, I want to model the beliefs and observations that this model is operating on, these other agents are operating on. So this is what can they see in the world? What are the sort of beliefs they have about the current state of the world? I want to model what are their goals and desires in that world. That might be different than mine. Maybe we don't have a shared goal. And I also want to model what are their actions that they're going to take with respect to these observations and goals, right? And so what are the kind of questions here that we need to estimate answers to? So first, what is the information that other agents are operating on? So this includes questions like, how do they perceive the world in general? Do they have access to the same percepts, or are we in some weird state where like maybe I see a full color view of the environment, they only see like a black and white view or something like that. So maybe it's in my best interest to model what are the sort of percepts that other agents have access to. Given an environment state, how might their perspective on that state influence their perception? So for example, here I'm showing a data set that we had last year for this multi-perspective task where we have, is this visible to people on the right here? So, okay, so we have a big room. So this is like in a house. And we have two agents in that room. We have a speaker and we have a listener. And we have a number of objects to refer to. So we have 3 different colored balls. One is blue, and then 2 of them are red. And the task of the speaker is to refer to the blue sphere under the knowledge that the listener actually doesn't know which of them is blue because it only sees red spheres. All of the spheres appear to be red. So the task is to write some kind of referring expression like the blue ball is the ball near the basket such that the listener can identify which one is actually blue. And this is a setting that we'll talk about a lot going forward. It's called like a reference game setting. It's kind of one of the simplest multi-agent games. And in this particular data set, we add a little twist to this, which is that the speaker has one view of the environment, and the listener has a different view of the same environment. So here, the speaker sees the listener right sort of in the middle of their view, and the listener sees the speaker right sort of in the middle of their view. So when the speaker is generating a referring expression, they have to take into account what they think the listener might see from their perspective. Right, so it's sort of like me talking to you now. I can refer to the screen on the right, even though it's on my left, right? It's exactly that sort of thing. So that's something that is really important for us to model if we want to, take into account what it is that other agents in the world have access to in terms of information. Another question is, how do they actually build their own internal model of the world as they are acting and observing in it? So as we're acting and observing, we might be building, for example, a spatial map of the environment. We saw some examples of that yesterday in the robotics talks. Other agents might be doing this too, so it might be in our best interest to also think about or model how those agents are doing this. Okay, another form of information that might be useful is, what are the goals that these other agents are working towards? Do they share the same goals as me? Are their goals just orthogonal? They have a different goal? Or are they actually, trying to compete with me or sabotage my goals? So there's a really nice example of sort of an environment that goes between, fully collaborative and fully competitive games, which is this negotiation environment, first proposed by Mike Lewis back in 2017 as this sort of deal or no deal task. So basically you have two agents. Each of them have their separate value functions, which is sort of how valuable are different items to me. So for example, you can see that here the person has a value of 1 for books, a value of 5 for hats, and a value of 1 for balls. While in this case it's ChatGPT, but another agent has a value of 3 for books, a value of 4 for hats, and a value of 0 for balls. And so you, as an individual agent, want to maximize your reward, right? You want to maximize the value you get. And because there's only a limited number of items in total in this environment, you have to negotiate with the other agent about who's going to get what items in the end. And you do that through a natural language, conversation, right? At the end of your interaction, once you've decided, this is what I'm going to take, this is what you're going to take, we're going to add up our scores, right? So each of us gets some end-up value, which is, the multiplication of how many items we have of a particular type times the value to us. And there's different ways that we can modify the overall objective to make this competitive or cooperative. So we could say that we both get rewarded by the sum of our income at the end, right? The sum of the number of our values. And that is going to incentivize us to figure out what are our value functions and who's going to get the highest score. How can we maximize our scores together? But we could also think about a competitive version where we, as individual agents, are rewarded by the difference in values. So I want to get the highest possible value, and then I want to subtract out the value that my competitor has, and that's what I'm trying to maximize. So you can see how this game could be either competitive or cooperative, and this is going to influence, how the conversation proceeds, right? So in the fully competitive setting, I might not want to reveal, or maybe I want to lie about what items I have. Or what is valuable to me. So in practice, what this later work found, which was out last year from Berkeley, is that if you do some kind of training in these scenarios in the collaborative setting, you have long and interesting conversations, maybe not super interesting, but long and sort of coordinative conversations. But in the competitive setting, the conversations are rather short. Okay, a third question of what we want to model here are how do other agents actually act towards their goals, right? So two underlying questions here might be, what are the skill levels of other agents? Even if we fully knew, here's their goals, here's their observations, we don't necessarily know how could they actually achieve their goals, right? What are the strategies that they're likely to take? So on the right here, I'm highlighting this work from last year on agents for tutoring. In mathematics, where you have some teacher and you have a couple of different students, and these students might have different levels of sort of knowledge in terms of how to execute different problems. And it's really, as a teacher, in your best interest to model what are the skills that these students have access to, because I want to be able to teach them in a way that makes sense to them. Another example would be, if other agents have more affordances than I do, other capabilities, then I might want to delegate work to those agents that they can do better than I can, right? And then a fourth question that comes up here is, how are other agents reasoning about me? So if it's useful for me to reason about other agents in the environment, they're probably reasoning about me too, right? So what is their model of me and their expectations over my behavior? And how does this influence the actions that they take? So one way of, one very related concept coming from like psychology is theory of mind, reasoning, TOM, reasoning. Here I'm showing an example of one of these theory of mind tasks. It's also called like the Sally-Ann task for understanding how are we modeling the beliefs of other agents as we're observing their behavior. So we have this little story. Jackson entered the hall, Chloe entered the hall, the boots are in the bathtub, Jackson exited the hall, Jackson entered the dining room, and Chloe moved the boots to the pantry. So there's a couple of different questions we could probe into our agents to see whether they understand this story. So first, what were the initial conditions of this environment? Where were the boots at the beginning? The reason this is ungrammatical is this particular data set was entirely synthetically generated. So where were the boots at the beginning? And then a reality check of like, okay, did our agent update the state after it observed this trajectory? Where are the boots now? We can also ask about our agent's beliefs about other agents. So for example, where will Chloe look for the boots? So we know that Chloe moved the boots to the pantry, so Chloe likely knows that the boots are in the pantry. But we can do this sort of second order probing as well. We can ask, where does Chloe think that Jackson would look for the boots? Because Jackson exited the hall before the boots were moved, then Jackson probably doesn't know that they've been moved to the pantry. So Jackson will probably look for the boots in the bathtub. Okay, so we talked a lot about these different sort of questions that we need to estimate answers to. How do we actually estimate these answers? So what are the tools that we have for bridging these gaps? When it comes to sort of bridging the gaps in like working towards a shared goal, we might want to coordinate our actions toward that shared goal. So in some environments, for example, we could reduce some redundancy of action. So there's this game that I worked on in my PhD called Serial Bar, where we had two agents working towards this goal of picking up sets of cards. Both of the agents could move in the environment. One of them had more steps per turn than the other, so it was in the best interest of them to get the one that could move farther to do more work, right? So we want to reduce redundancy and maximize efficiency through coordination of our actions. Other environments might actually require us to coordinate our actions in order to solve this task. So one of the, I'll show some examples from this environment later, but I don't know how many people here know the Portal series as video games. Okay, yeah, not very many, which is kind of surprising to me. But because it was like a very popular game, but maybe like, yeah, maybe I'm showing my age. So it's like this puzzle game where you, and there's a co-op version of it, where you and another player have to coordinate your actions to solve puzzles. And in many of these puzzles, you literally could not complete them unless you have another person in the game, right? So you have to learn how to coordinate your actions. So again, what are these sort of the questions that we're trying to estimate answers to? How can we more successfully coordinate our actions, especially in unfamiliar environments? How can we better model these other agents about like what they're observing, what they are trying to do, how do they take actions, what are their skill levels? And then also, could we influence other agents in the environment? Could we influence them in terms of like sharing information with them, or telling them what they should do, or telling them how to achieve their goals? So how do we do this? Well, one really good way to do this is through using communication and language. So what can we do if we have language? We can coordinate on shared plans. We can share information with each other. We can ask questions to resolve our uncertainties. We can teach people something. We can tell someone what to do, et cetera, et cetera, et cetera. So many things we can do with language to sort of bridge these gaps that I mentioned before in terms of modeling other agents in an environment. So I want to go through an example of like really step-by-step example of what does it mean to use language in these kind of multi-agent environments. So let's say, I'm in front of this like shelf and my goal is to get the suitcase. So I want this yellow suitcase at the top, but I'm too short to get it. One of my observations could be there's this other person, this green person, who is tall enough to reach the suitcase. And so maybe the optimal action for me to achieve my goal is to get the green person to give me the suitcase, right? But I also believe that the green person doesn't know that this is my goal. So the green person is not going to just give me the suitcase, right? Unless I do something, unless I take some action. So how can I get the suitcase? I'm going to make an assumption that I share a lexicon with this other person, with the green person. So there's a number of items on the shelf. There's a yellow suitcase, a red suitcase, and a red hat. And there's a number of different ways I could refer to these things that I know, and I believe the screen person knows. So for example, I know that suitcase could refer to the two suitcases. I know that hat could only refer to the hat. Red could refer to either the hat or the red suitcase, and yellow could only refer to the yellow suitcase. So I believe that the green person also knows this lexicon and knows that I know it, and so this isn't the common ground. This is something that we both know about each other. So I should choose an action from this lexicon that my listener can use to infer what my goal is. So if my goal is to get the yellow suitcase, some of these actions could include the word suitcase, some of them could include the word yellow. But I might want to choose, an action that could uniquely let this listener uniquely identify my goal. So I don't want to say suitcase because that could also refer to the red suitcase. So maybe I want to say yellow suitcase. So I could say something like, please hand me the yellow suitcase. But I can also reason about what else this green person knows about me. So this green person knows that there's a red suitcase right there, and I could just easily grab it. So maybe I actually don't have to say yellow. Maybe I could just say, please hand me the suitcase. Please hand me the suitcase because, I wouldn't be asking them to hand me the red suitcase because I can just do that myself. Okay. Sorry, this is like lagging a little bit. But I could also reason there's a red hat right next to me too. I can also, the green person sees that I could also grab that. So maybe I don't even have to say suitcase. Maybe I could just say, please hand me the, or whatever, and then maybe the green person already knows, well, I'm just going to hand this blue person the only thing that they don't have access to, right? So this green person is I believe that this green person is also trying to figure out what my goal is, and therefore I can be a little bit lazy with what I'm saying. Okay, so let's show this example again of how we're defining our agents. So we have some agent pi, and I take as input observations. I also take as input the utterances that all of the other agents are producing. So all the other sentences that they're writing, for example, up to n-1 because I'm the nth agent. And then I also take into account my goal. And then my output space also includes utterances. It's not just actions. I'm not just moving around. I'm also producing language, right? And the interpretation and production of utterances here, so the ability for me to understand what other agents are saying and produce intelligible utterances, is scaffolded on top of this shared communication protocol, like the lexicon I showed with the suitcase, with the items and the words. So yet another challenge, and this is the last main challenge of multi-agent systems that I want to highlight, is that interactions are incredibly dynamic. So at the beginning of an interaction, we might start with significant uncertainty over the other agents in terms of what they know, what their goals are, what their skills are, etc. But we also have uncertainty. Sorry, this is lagging, I think. Oh no, it's doing that weird thing where it's not updating on my laptop, but it is updating on here. Okay, I'll just look at this then. But we also have uncertainty over how they use language. So what is the lexicon that they think I have? I mean, I think actually a really good example is I don't speak French, but I'm here in Montreal, and I guess I assume that everybody here kind of also probably speaks English, but there's sort of this negotiation of maybe they have uncertainty over whether I can speak French, and so we come into the interaction and they say bonjour, hello, and I'm like hello or whatever, right? And so there's this uncertainty over what is our shared language, for example. And so that's a big source of uncertainty here, and we want to over time reduce this uncertainty to make this interaction efficient and effective. One way we can do this is converging to more similar representations. So like I've talked about before, we want to build models of one another by observing their behavior, but we also want to explicitly resolve, or we could explicitly resolve these uncertainties via language use. And this refines our expectations over other agents and their behavior and the way that they're going to use language. And by having certainty in our expectations, we can take communicative shortcuts. So for example, if I say originally hand me the yellow suitcase, and then I say hand me the green suitcase, and then I say the blue one, and then red, by the end of this, you know probably that when I just say red, I am asking you to hand me the red suitcase, right? Now, if I had started this by saying, open the yellow suitcase, open the green suitcase, the blue one and the red, then red here would mean open the red suitcase, right? And so we formed this protocol over the time in this interaction that is, if I say the color of the thing, then like I don't have to say, hand me the red suitcase, hand me the red suitcase. I don't have to say the whole thing because we've established that the convention is now that I'm asking you to hand me things. So one perspective on this is that we are learning in interaction, right? So our agent policies are adapting as they learn about other agents. This influences the observations that other agents make of them, which is in turn going to influence how other agents adapt to us. One example of this that I really like is convention formation in iterated reference games. And we actually just saw an example of convention formation with the different suitcases, where the convention was that, we're just handing things to each other. So I'm gonna talk a little bit more about reference games in more depth soon, but the general premise is that you have two people, you have a speaker and a listener. The speaker and the listener have access to the same set of objects, but they are in different orders. And the speaker's job is to get the listener to select the right object at any given time. So if the speaker is trying to get the listener to select this object here, the one in the top middle, then they're going to write some kind of referring expression, send that over to the listener, and then the listener can select an object that they believe the speaker is referring to. And in some cases, you can have a little bit of a dialogue. The listener could ask a question, that sort of thing. In an iterated reference game, we do this multiple times. So we have the same set of objects. We go through them. We go through the set once. Then we reshuffle them, we go through the set again, and then we keep doing this like 12 times, for example. And over time, we see evidence that the players are forming conventions about how to refer to the items in this set. So, for example, one of the clear evidence that this is happening is that the references are getting shorter. So if we do this 6 times, so we take all of the items, shuffle them 6 times, play the game 6 times with those same items, and we look at the number of words that are being used to refer to the individual items, that is getting significantly shorter, from like an average of 15 words down to like less than 5 words. But one of the things here that is important to observe is that they're not just getting shorter to the same point. We're not just referring to this, using the same word to refer to each of these tangrams across the entire set of games. In each game, in each pair of people, we will converge to maybe a unique sort of convention. So, this is showing an example of how different pairs of people, each line here is a pair of players, go from at the very beginning to the end of this game, how they change the language they use. So we see, for example, for this little abstract figure on the top right, a lot of people, so the green lines are like calling this a ghost, for example, and maybe they start with this instruction or this referring expression, a ghost flying to the left with arms outstretched. And then a number of pairs here, maybe like 6 or so pairs, ended up calling this a ghost in the end, the last repetition of the game. But other pairs ended up converging on flying or YMCA or things like crazy arms. So there's a bunch of different ways that these pairs of people could converge to a particular way of referring to each of these individual items. And the important thing I want to highlight here is, if you get placed in this interaction at the very end, if you suddenly swap people and you're paired with someone who has formed this convention, falling, then you might not have any idea what they're talking about when they say falling, because that was not the convention that you formed. So the conventions that are formed through the interaction become interaction specific. And when we're talking about multi-agent systems, like we suddenly lost all of the sort of resolution of uncertainty that happened in the interaction when that convention was formed. So that's what makes this multi-agent situation really hard, is each time we do a rollout, we sort of roll out into this very specific space that is not necessarily easy to get back if you do another random pairing of people. Right, so So this means that this problem is very difficult to model. Agents need to model not only their first order policy, which is getting their goals executed by taking actions, but they also might need to model how their adaptations, how their actions are influencing the adaptations of other agents. So for example, if I introduce a new shared abstraction, like a new word like flying, or maybe a new concept, like an abstract like concept, this happens a lot, for example, in like political sort of dialogue. For example, when people are talking about policies, people will introduce a new concept, and then that becomes something that the group can refer to, and it also changes sort of the perception of other people. But that's what makes this a very difficult to evaluate setting. So the dynamics of an interaction depend on many more random variables, not just sort of the stochasticity of the environment, but the uncertainty over the variation in agent partners, right? So, the distribution over humans is like huge, right? It's a very long tail distribution. If you take two people from that distribution, like every sample of two people is going to be very different from each other, and we're going to end up with very different conventions formed. We see this also when we're looking at human agent collaboration. So, for example, this is a study that I had a couple years ago where we had people interact with a natural language instruction following system over the course of a couple of weeks, where we deployed the model, I think, about 12 times. So we start with a model that was pre-trained, and we do some training in the loop, right, where we're learning from the human behavior. And what we find is that if we deploy the very, very first model policy, the pre-trained model, at the end of this experiment, alongside the one that's been fine-tuned, we see that actually the model is performing better. It appears to be performing better. So this very same model, like this is, theta 1, that's the very first model parameters. It hasn't seen any data that the other theta 11 model has seen during training. We see significantly better performance, which is really strange. But when you look into the data, this is because the humans who are actually giving instructions to this model have changed how they're instructing the model. They're giving it like shorter and more easy to understand instructions, for example. So the people here in this experiment are adapting to our model because they've observed that it has its flaws and it has things that it is good at. And so when we're doing this experiment, we can't just say that this improvement overall is because the model policy is better, because it's also influenced the fact that like people have changed their expectations. So this is something that is really important to keep in mind, right? Like in doing these sort of experiments, if we have these human in the loop settings, are the dynamics that we're observing, for example, improvement in performance, because the model's actually getting better, or is it because people are adapting in interaction? Okay, so now I want to talk about some. Actually, first maybe I'll ask if there's like any questions or things like that. Yeah. Uh-huh. Yeah. So the first question is, do maybe I don't know if I want to rephrase it as like, do we need to have goals? Yeah. Yeah. Right. Yeah. 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 Oh, so I don't think that in all settings you like, because sometimes you come into the interaction and you know that you share a goal, and so having modeling exactly what the goals are of other agents is not necessarily important. Yeah. And I think that like my formulation here is not necessarily like the default like RL formulation, because a lot of the time the goal is implicit like in the reward function. We're not actually conditioning the model on some explicit representation of a goal. But I like thinking about it this way. It also connects to this sort of belief, desire, intention model of like cognition that that's like pretty popular. So so the second question was, oh, and memory. Yeah. I mean, so I think in practice, like people do different things in terms of like what like history you have access to. I think like does your state include the history, or is it like actually Markovian where it just includes what you have now, and you've sort of embedded the history into the model parameters. um, I think this is like an open sort of question, or like design decision sort of question, where I think people do different things and have different expectations over what is the like scope of the agent itself. So you could think about, and I'll talk about some examples where the learning through interaction, the sort of like learning of a protocol or establishment of a communication protocol is implemented as like gradient descent. Um, and so like we as the model developers are like, okay, model's not going to be conditioned on the prior interactions. We're just going to let that come through in the fact that we're like training them to establish a protocol. But maybe one expectation we want to have instead is that the models themselves in like their parameters support the formation of conventions in new interactions, right? So we don't actually have to use gradient descent to do that sort of communication protocol establishment. Instead, we just expect that if we deploy our model in interaction, it should be able to handle that convention formation by having access to like a sequence of previous turns and things like that. So there's just different expectations that people have over these models. Yeah. I think in practice, there is a really interesting question of like, can we train a model that can do this sort of in context learning in order to like actually interact in like a natural way by forming conventions and like learning about other agents without us saying like explicitly like you have to do gradient descent to understand other agent goals. But a lot of like standard multi-agent RL, which I'll talk about a little bit, and then we have Natasha Jacques, who is probably going to talk about it a lot more, is this sort of paradigm of we have one agent, it doesn't have access to the history, but we are still like training it to interact by implicitly embedding like the goals and sort of actions of other agents in the parameter space. Okay, cool. So I want to talk a little bit about like oh yeah, sure.
Or what happens in LLMs, it's the opposite. As the agents are trained more with human interactions, the length of their responses keep increasing.
Mhm.
So it seems like a very different thing. These are artificial agents. In one setting, they are
Yeah.
coming up with shorter language. In the other setting, they're coming with longer and longer language.
Yeah, great question. So there's like I think the simplest reason for like shortening of conventions is like efficiency. So we don't have to be redundant if we believe that the other agent would understand us by being shorter. And so if we can, so there's this concept of common ground, which is sort of this modeling of what we believe other people know and what we believe they think we know as well. So this is sort of like infinitely recursive like set of knowledge that we both think we know. And by making use of that common ground, we can be more efficient. So if we assume that like by saying ice skater, I will like we know jointly that that'll get us the right object in the reference game. There's no reason for me to say the thing that looks like an ice skater pointing to the left or something like that. In terms of like RLHF, I think this is a very different paradigm where this is more like the multi-agent RL setting where the model doesn't have access to this previous context. It's just incentivized to it's not operating on incentives. It's not operating on any goals. It's just how are we shaping the distribution of outputs in the LLM. And when the training data gives higher rewards or higher preferences to longer responses because that's what people like, then of course the output distribution of the LLM is going to change to that. And I guess one way of sort of bridging the gap between these two is that RLHF, or at least standard RLHF, is not in a sort of game, like the incentives around RLHF don't have the same communicative pressures. I've thought about, like, it could be kind of cool to see, like, could you also implicitly incentivize shorter responses by like asking people to give RLHF judgments as quickly as possible, for example. But yeah, I think it's an interesting question. Yeah. Okay, and then moving a little bit on to like what are those communicative pressures and how do they relate to the environment? So there's a lot of different environments people use to study these multi-agent systems. So I'm going to talk about some elements of interaction design that are relevant here, some commonly used multi-agent games for studying, human-human, human-agent, and agent-agent interaction, and then I'll talk briefly about conversation itself, sort of as a multi-agent game. Okay, so a couple of different elements of interaction design I'm going to go through. Let me check my time. I think I have, yeah, okay, cool. I'm going to go through like relatively quickly. So we have incentives. So what are the things that the agents are working towards? What are the constraints and affordances that we get from the environment itself or the communication channel? And then who is it that is participating in this interaction? Who are the other agents? So in terms of incentive design, we have this, I talked about this a little bit before, we have this continuum between a fully collaborative and a fully competitive game, and so I talked about this negotiation game before. There's also these incentives, with respect to like what do we know about other agents' incentives. So this is, again, this is also, actually I didn't mention this before, but this is related to the sort of AI alignment problem where like we want other agents in the environment to have the same goals as us, and how do we make sure that they do by training them or instructing them. Another form of incentives here is sort of the interaction length and the timeline that it operates under. So there's this interesting work in teaching, again, where the goal is to get an agent to do something, to learn something new. In this case, we're teaching an agent which mushrooms are poisonous and which ones are good to eat. And depending on how long a human knows that the interaction will continue, so for example, oh, we're just going to do this one episode and then we're done, versus the machine is going to go off and like collect mushrooms for 10 years or something, there's going to be different ways that we instruct that model. So we could either instruct it via demonstrations, just saying, okay, the red one is good, the blue one is bad, or we could say, like, if you do like if like the spotted ones are generally good unless they're green, in which case, like, so if you have a more complex and expressive and abstracted instruction, rather than just showing a demonstration of a specific mushroom, then we can train the model that this gets our learners to operate over a longer time horizon. And then, of course, there's like this sort of implicit task difficulty due to like time constraints, due to the sort of computational reasoning complexity, novelty of like things in the environment. So, do I and my partner have to like figure out how different objects work? And then also things like risk. So one example of an environment that's been studied within the multi-agent RL community is Overcooked, where you and another agent, or I think there's actually versions that have multiple people too, more than two agents, are trying to quickly make dishes based off of orders that are coming in a restaurant. So you have to respond really quickly to these requests. And one of the best strategies is just to sort of a priori decide, like, okay, that's your role. I'm going to do this. You're going to do that thing. And then we're just going to, like shout things at each other when things come in. In terms of risk, there's this interesting game called Chained Together, and there's other games similar to this where you and another player are trying to climb up as high as you can on this like sort of increasingly unstable like structure, and you are chained together, which means that if one of you falls, then like the other person's going to fall too. And so there's this like very high risk of completely and once you fall, you start at like you can end up starting at the bottom too. And so there's a lot of risk in this game, and so you really have to be careful in coordinating with each other so that you don't both die, basically. And then there's other contextual factors outside of the game itself that might make people perform differently or agents perform differently. When we're doing something like crowdsourcing, we have to think a lot about how are we paying participants, and how is that pay tied to their performance. If you're interested in this, I had a tutorial back 2021, I think, where we talked about crowdsourcing design and like how do we design incentive structures that really get us the data that we want out of our crowdsourcing. And then there's social factors. Like we had this, I'll talk about some of our data soon in a minute, but we had this study where we got a bunch of people to play the Portal game together. And one of the things we noticed is that even though everyone was strangers to each other, they were all talking about stuff that was like outside of the game, like boba shops and like what their research was about and that sort of thing. And we're like, this doesn't mean that, like, this doesn't help you play the game, but there's these external social factors where like it's like good and fun to be friendly with other people. And then also, is the interaction fun? Like, is it a fun game? That's going to influence how our human participants will interact in these environments. There's also factors with like the environment itself. So we could have like continuity in action and perception. So for example, we might have games we have to respond really, really, really quickly. So we have a very continuous sort of time. So like Super Smash Brothers is an example of this. Or we have games where you have a really complex action space, like for example, a flight simulator. We also, games have different forms of embodiment. There are 2D games, like Pac-Man is a very simple 2D game where you have a single map, a single maze here, and the only things that are moving are like the enemies and you. We also have these more complex 3D games. One is like Satisfactory, which is also could be a co-op game where you are trying to create a factory that's like creating a bunch of different resources, and this is like a pretty complex looking environment. So you have a lot of complexity in terms of like understanding where you are and like what is going on around you, and so it's a pretty cognitively complex environment. A lot of people also study these ungrounded, quote unquote, ungrounded game like text-based games like Zork, for example. So this is a really popular setting for studying multi-agent systems as well. What are the sort of like, this is more about like incentives than environment, but like, do we have an open world so that you can do basically anything like Minecraft? You can go anywhere, you can build anything, or do you have a more guided environment where you have like a very small action space at each step? And then there's also this element of what is and isn't in the common ground, in the common perception. So on one end of the spectrum, you have a game, for example, like Pico Park, where all of the players see this exact same perception, right? So nobody has different views of the environment. All you see, like everybody sees the same thing. Or you have games where they're explicitly designed to make the environments look different. So there's this game called Bokra, where it's another co-op game, but you and your partner see very, very different things in the environment. So this is the same state, just 2 different people. And like on the left, you have this nice forest, like lovely little forest. And on the right, you have some kind of like dystopian robot future thing. And you're both working in the same environment. There are elements that tie these environments together. So if I do an action in the beautiful forest, it's going to influence my partner's environment state. But we don't know exactly what other people see in this environment. So we have to bridge that gap with language. And then, like I mentioned earlier, games have objects that we've never seen before, and they behave in ways that we've never observed before either. So, for example, in Portal, you see these like little tube things. These are actually don't remember what they're called in game, but like they move you. If you're in that tube, you're going to continually go in one direction or another. And that's something that even if you were in a single player game, you're going to have to spend some time to figure out those dynamics. But if you're in a multiplayer game, maybe your partner has had experience with this before and can teach you how it works. So that, it's sort of the multi-agent setting can facilitate that. Okay, we also have, different participants in an interaction. So one very clear dimension of design here is like how many people are there and what is their sort of social structure outside of the game or in the game, right? So, a 2-player game is going to be very different from like a 3-player game or like a 100-person player game. Do these people have separate roles? Do we have like a leader-follower setting? Do we have like an instructor who's teaching someone something? Do we have a user and then like a computer agent? Or do we have like no roles to start with? And maybe that's something we have to figure out through conversation. We also might have asymmetries. We've talked a lot about asymmetries before. We might have asymmetries in our knowledge and our observations, the things we can do and the things that we can see. And asymmetry itself can come either ephemerally, so for example, at a certain point in time, you might have different perspectives, you might have partial observability, or it might be absolute, where like we really have these absolute differences. I know how to do something, you don't know how to do it, and so we have to bridge these gaps differently. And then finally, in the communication channel, right? So what is the medium of communication? In a fully embodied scenario, we have voice and vision. Maybe we have, gesture and sort of body movement, that sort of thing. Maybe we have only voice available to us, and maybe we have some amount of like proximity chat where like, in the video game, like you might be really far away and there I can't hear you, but if you come closer to me, I can hear you. A lot of games are like text only, so you're just communicating over natural language text. And then there's also signaling situations where like the game has a really restricted communication channel. So there's this game called Journey where I've not played it before, but I watched this really nice video about someone playing it with a stranger. And the only communication that you could ever do with these people is like ringing a little bell or something like that. And there's this this nice like video where this guy was talking about, I went and I saw this stranger there, and like we started playing together, and we like formed this convention over like how we were using the bell. And I thought it was just really, really cool, right? It really exemplifies like the fact that we can like really form these conventions in very like creative ways through interaction. And then what are the sort of dynamics and affordances that our communication channels give us? Do we have some enforced turn taking in as we're moving and talking, or are we talking simultaneously? Is there latency in our in what we say? Is there noise? Like, is the communication channel really noisy? And is there asymmetry in who can say things? So like in Serial Bar, only the leader can send things to the follower. The follower cannot speak back. And is there feedback? Like, oh, I guess this is the asymmetry. Is there feedback? Can our listener like respond to the speaker? This is a paper from the 60s, some of the very first work on like reference games, empirical work on reference games, where they find that if the follower or if the listener has the ability to ask questions or give feedback to the speaker in a reference game, we do see these convention formation, reduction of utterance length. But if the listener can't do anything in response to the speaker is just going to always be very, very like lengthy in their referring expressions. Okay, so we talked about incentive structure, constraints and affordances on the environment and communication channel, and the participants that exist in an interaction. So I'm going to go through a couple of multi-agent games that have been studied and are used to study this work. The very first, like very simple multi-agent game, the simplest, I think this might be the simplest form of an multi-agent game, is a reference game. So in this game, we have a number of objects. In this case, we have a couple colored squares. So we have an environment, which is a set of candidate references, and these are available to both of the players. We have two players. We have a speaker and a listener. So the speaker knows the identity of the target object, and that's the one with the arrow pointing at it. The listener does not know. They only see the three colored squares. Their shared goal, and they know like this is in common ground, is that this is the goal they're trying to achieve, is that the listener should pick out the target object. And the only actions that they have to execute is the leader generates a referring expression, a reference in natural language, and then the listener's action is to just select one of these objects, right? So maybe our speaker says purple, but in that case, our listener is going to be, have some ambiguity over what the possible actions are that they should take because there's two different purple squares. So maybe our speaker wants to say dark purple, in which case, yes, the listener would, grab this dark purple square, and then we can measure success of this interaction by having, us check was the thing that the speaker intended selected by the listener, and here, yes, so we've succeeded. We've earned. We've gotten rewarded for communicative success. But we can also say, we don't have to say, dark purple. We've had an example of this before. So the speaker should, we want our speaker to estimate the listener's interpretation of possible utterances. And our speaker might be reasoning that the listener is reasoning about them. So even if there are two dark colors, the speaker can still use the word dark to refer to just the dark purple, because the speaker believes that, the listener believes that if the speaker wanted to refer to the green square, they would say green, right? Because that's the only green square. That's the only thing that could be referred to as green. And by saying the word dark, the speaker has chosen an utterance that could refer to multiple squares, the dark green or the dark purple. But the speaker shares the goal of efficiently getting the listener to pick out a target object. So the listener knows that the speaker is trying to communicate something. And so using an ambiguous utterance is likely intentional. The speaker is probably not going to the speaker is probably not trying to confuse the listener. And because the green square could alternatively be referred to as green, but the dark purple square cannot be uniquely identified as purple, then dark probably refers to the dark purple square. Okay, so now we have this really sort of complex recursive reasoning that allows us to choose this as a really efficient way to refer to the target. Okay, so reference games have an extremely simple objective, which is just, can we select the same thing? And the information asymmetry is also really, really simple. Speaker knows something, listener doesn't, and we can bridge that gap by saying something, a single reference. But it can elicit this really sophisticated theory of mind reasoning about other agents. And this is a game that's been really well studied in cognitive science and psychology and linguistics since at least the 1960s. So these are the original objects that were used in this work from Krauss and Weinheimer back in the 60s. And we also have a lot of work that shows this is still a challenge, right? So this top paper is coming from Joyce Chai's group on evaluating whether LLMs or VLMs can efficiently generate pragmatically optimal references that uniquely identify objects in an image. And at the bottom, I'm showing a paper, a highlight from a paper from Yov's group on whether these systems can establish conventions with human users over time and interaction. And they find that without heavy prompting, they cannot. Okay, so there are also environments that people have studied for a long time with when studying and building multi-agent RL systems. So for example, Melting Pot and Melting Pot 2.0, which are hand-designed game environments for evaluating and training these agents that have these physical environments, 2D environments, and then some background players, other agents that are going to be in that environment. And the incentives and the interaction design here is coming from work in economics and game theory. Some other examples include things like the StarCraft competition. Overcooked AI is a simplified version of Overcooked that people have used for this. And then Hanabi, which is a coordination card game. Okay, so there are also a number of multi-agent games that have been studied that require the use of language. So these previous ones, I believe, people don't study language use here. But we also have a lot of interesting games that people have used that include instruction following. So this draw me a flower task is this drawing task where one person's instructing the other to draw something. Similarly, we have the Minecraft dialogue corpus where we have people instructing someone to build something in Minecraft. The Mr. CAD dataset is a recent dataset. I think it's really cool where you have one person who has this CAD design in mind, and they're trying to communicate it to a listener who's creating that design. And the architect here, the designer, is instructing them not just with language, but also with sketching. So they can correct someone's design by sketching on top of it. And then Serial Bar is another example of this, where one of the players is generating instructions and the other one is just following those instructions. But we also have multi-agent collaborative communication games that are conversational, where agents are sending and receiving messages jointly. So we have a game, this is the cards game. This is an older game from Chris Potts' group, where you have two agents in a maze, and they have different asymmetries in terms of what they can see, because there's partial observability, and they still have to pick up sets of matching cards. So they do this through a natural language conversation. Another example is this recent work on decision-oriented dialogue. I don't remember exactly what they call this setting, but where you have two agents and they have this shared task of, for example, planning travel together. And so the goal is you have this database, you want to find the best optimal travel plans, and you do that through a conversation. And then this is another recent work from Alexander Koller's group at Saarland University, where the goal is to solve these constraint optimization problems, these NP-hard problems, by having a conversation between two agents. Okay, I want to talk about some of our upcoming recent work that we worked on that looks at the Portal 2 game, like I mentioned before. I realized I do have sound, so hopefully it works. So we have two players. they have symmetric roles and affordances. They have a shared 3D world, continuous control and perception, novel objects, and world dynamics. And then their goal is to exit a room while avoiding hazards. So let's see if this works. Whoops. So this is like a tutorial of the first game. Oops. So maybe I can just put my headphones. I'll just put my headphones down here. That's always how it works.
This testing course was
Sorry.
again. Hello again. This testing course was originally created for humans. It emphasizes teamwork.
Can you hear this?
Unlike us, humans need to be taught teamwork. Orange receives 5 science collaboration points. Excellent.
Okay.
Although great science is always the
Okay, so they're working together to solve these puzzles. That was like the very first puzzle, so it's like a pretty easy puzzle. I'm going to show an example of a like slightly more challenging puzzle, and this is actually coming from the data that we collected. And I'm let's see how much time I have. Okay, and I might pause and show some examples of some really interesting like language use and coordination that's coming from this interaction.
This button is where we get cubes. Can we get more than one?
Usually not.
Okay.
Yeah, that just exploded our cube. Okay, so I can put a cube over there.
Yeah, maybe just point it at different things. See.
Let's see what happens.
Okay, so
Oh my god, you should be.
So
okay.
this button is
So-
where we get
I don't know,
cubes.
the order on this is weird. But one of the things I wanted to highlight here is that at the very end, they're completing each other's sentence, which I think is really interesting.
So
The
Okay.
you should be in charge. Too much responsibility. Okay.
so that
So here they're negotiating who's going to do what. They're negotiating their role.
one
Do
goes up.
that. Where are the different areas where we can? Oh,
Okay, and here Blue, interrupts herself when she notices like this is the area where we can do the thing that we want to do. And so you don't have to continue your sentence because it's clear to you and the other person what you were going to say anyway.
interesting. There's a
I'm
panel
gonna go
there, but we cannot do anything. How do you get into that? Oh, we have to get over there.
Where?
So.
Okay.
Okay, so here, Blue is saying, oh, we have to go over there. Orange is, there is very ambiguous. So how does Orange figure out where there is? They ask where. Blue doesn't say anything. And then Orange is like, okay, where was Blue looking when they said we have to go over there? So they follow where Blue was looking via gaze tracking, and then are like, oh, that makes sense. That's where we need to go. So because they're embodied in the same environment and you can actually see where each other are looking, that actually makes communication a little easier, right? Because you can, one of the very most basic communication forms we have access to as humans, and actually where a lot of language acquisition comes from, is following each other's gaze and attention, right? And so that's something that if you have these embodied environments, you can elicit, right?
We pointed.
Oh, I think we have to yeah, okay, we're gonna have to, one of us is gonna be, okay, you be the pointer, because clearly I have
Okay,
natural
I will
knowledge
try.
to that.
Okay, so here, Orange says, let me point it here, where point is this completely new concept of, taking this cube with like a glass in it and making it move the laser in a certain way. And then Blue says, okay, you be the pointer. So now has created this another abstraction, which is like pointer is now a role. So Orange is going to be the pointer. And I think for the rest of the game they played, Orange was always the one who was doing the pointing because Blue didn't know how to do it.
Yeah, so, okay, and then I'm gonna.
You go on the little path.
This.
Okay, I'm gonna do this.
Okay, uh-oh. This
It's
seems
not
like
gonna kill
we're
you,
gonna
right?
die. It
Is
Seems
it?
like I'm about to die.
Okay,
No,
I
wait,
will.
I don't know how I'm supposed to get to the other
Ow.
side. Oh wait, here. No wait, I got it. Portal,
Okay.
portal,
Nice.
and then I just have to jump at the right time. Can you tell me when I'm supposed to jump? Oh,
You can jump
like
right now. Yeah. Okay.
Okay, and because they can act while they speak, we get this interesting aspect of like you can say things as you're doing them. So Blue here says portal, portal, which is an interesting thing that doesn't really come up until you have like this joint action and language use.
Okay.
Oh. Okay, I'll bring you all the way up, and then I'll quickly point to that one so you can go. Here. Is it going? I can
Yeah.
see.
Oh my god, I just
No.
exploded. I think I just exploded.
Oh no, my bad.
Oh man. Okay.
Oh, hi.
Hi.
Yeah.
Okay.
So usually when you say hi, it's like when you see someone for the first time. So I think it's really interesting that they do this here, right? It's like kind of like a joke, like you're coming back from the dead. Hello, So these kind of things happen when you have these like external communicative pressures to like be friendly with each other because you're both Berkeley students. Well, not because you're Berkeley students, but because you're like on the same campus together or whatever.
Okay, try this one more time.
Oh yeah. So here Orange says we'll try this one more time. And this I think has a really interesting meaning, right? Like what does this actually refer to here when we say we want to try it one more time? So they tried something already and Blue, like they failed, and so Blue died. So they don't want to do the exact same thing that they did. So this sort of is referring to like a shared goal potentially, but also partially something about like their strategy towards that shared goal. And I think it's really interesting that this is sort of something that both of these people really understand very clearly because they share a goal and a sense of the plan that was established maybe even without much actual conversation.
Oh, so I need to
I think you need to go like really fast.
higher. Yeah. Okay. Maybe if I put a higher portal to. Oh, like if I put one of my portals up there.
So here Blue is saying like I need to put a higher portal. Well, what is it? What is that comparing to? It's comparing to something that happened a couple minutes ago. And if if I'm talking about like building a system that would play this game, like this is a really long context thing, right? Like higher, there's a lot of spatial stuff here. What does it mean for something to be higher? There's two different portals she has to place. There's a lot of ambiguity here, yet the people are able to like understand each other, which I think is really cool.
Maybe raise that one up first all the way, and then try to hit this one. Does that make sense? Like go to the other
this one
first. Yeah, like
Okay.
because that one takes a long time.
Yeah, that's true.
And now.
So yeah, here Blue is talking about that one and this one, referring to like the different portal or like laser receptacles, and is asking to have Orange confirm that they understood. So does that make sense? Like go to the other one first. And then Orange sort of points at one of the portals and says, this one. And then Blue is like, oh yeah, that one. So these kind of clarifications really allow the two agents to bridge the asymmetries in their understanding. And that's something that like is only afforded by having this multi-turn, multi-agent interaction.
Switch it around.
Just time it. Okay, is it all the way up yet?
Yeah, now it is.
Okay, here.
Okay.
So we're.
Oh shoot! It's too.
Um.
It goes down too fast.
Okay, let me raise this one all the way up and then try this again. Maybe.
Oh yeah.
Oh, it goes
Wonder how
really
high
high.
I can go. Oh, please don't smush me. Oh no, yeah. Okay.
I'm not gonna smush. Oh, okay. Got it. I'm not gonna move. Not gonna move. Not
Okay.
gonna move. Here. I think that works. That works.
Yes, well done. Okay.
Let's go.
Okay, so they had this subtask of like getting Blue over to the other side, and once they finish that subtask, it makes sense for them to confirm with each other. Okay, we're done. So there's a lot of different ways we can say this. We can say that works, well done, let's go. And so that sort of thing is like very prevalent in this data set where we're sort of the players are managing what are the tasks they're currently executing, when have those tasks been completed, and we can move on to the next thing. I'm not gonna, they finished the puzzle. It takes a little bit of time until then, but yeah. That was the last thing that I wanted to show. Okay. I think that might be the end of audio, but I'm not sure. I'll redo it if not. Okay, so we have this new corpus. It's about 12 hours of gameplay, 21,000 utterances collected from 18 different pairs of people from the UC Berkeley campus. We know like their video game experience, which might influence how they play because maybe they've played the game before. For each gameplay, we have the observations of the people, so the screen recordings, the player audio, and also all of the actions that they are taking, which allows us to like replay the game. It allows us to do things like raycasting, so we can see exactly what observations the players had, and so that's really useful. We're going to release the videos and the transcripts publicly, and the audio will also be released under an agreement not to share. This was like coming from our IRB. Okay, so that was the Portal game. I think it's a really cool example, but just one of many possible games that we could be studying, these like really complex multi-agent games and multi-agent interactions. And so a lot of people, I guess, like we've talked that this is like a super embodied, very like spatially relevant game, requires understanding where you are, what things you can do, like physically. But going back to like the language side of things, LLMs are huge, obviously, and a lot of what we use them for is like conversation. And so I want to briefly talk about how we could cast conversation itself as a multi-agent game. And this is something that like a lot of philosophers and linguists and so on have talked about, in many for a very long time. And in conversation, we might not have like a physical environment that's relevant or even available, like consider like you're texting your friends or something like that. But we all still exist in like a social world. We have common or maybe uncommon knowledge. We have different goals and values. There's current events that happen, and maybe we're coordinating about something that might happen physically, like a party that we might go to or something like that, right? So we can still communicate even just over text, right? And it still has these communicative pressures. And one could work towards like social goals using language only as action. So we could educate people, like, just lecturing, for example. We can do persuasion. We can try to like persuade people to do different things. A lot of this action is negative. It's harmful too, like hate speech or like having dog whistles and things like this. So there's and some people have studied this setting of just text-only social communication as a sort of multi-agent game. So Zootopia is one example of this coming from CMU. Okay, any questions about like game environments and interaction design? Cool, okay, so I want to move on to talking about the systems themselves and how we might implement these things. So there's a couple of different broad stroke like ways that we implement these models. So one very clear one from like, we have LLMs, we can prompt them, they do instruction following pretty well, is we can just prompt them to perform, act as multi-agent systems. So, this is potentially the GPT-5 prompt extracted from some prompt hacking stuff. And I got it from, actually Dan Fried sent it to me from a Reddit post. And you can see that this system prompt is really instructing the model to take on a role, right? You are ChatGPT. You have personality V2. You are insightful and encouraging. Ask at most one necessary clarification question at the start, not the end. So this instruction is telling this system how to act as an agent in conversation, right? This is also coming from Yoav's group, which I think you said you're not talking about this work, so I'll talk about it in a little more depth. So this is, again, a reference game where we are trying to get a system to form a convention with a human player over time in interaction. And in order to get this model to actually form conventions in a way similar to humans, one of the metrics being like the length of the interaction, the length of the referring expression, which should be going down. I think the gray line is the human line. And so this last graph here is when they prompt the model with this very long instruction that's explicitly telling the model to form conventions. So you're playing this game. You need to think about how the information might change over time. You should shorten your messages. You should, extract salient tokens from the previous message rather than introducing new words. So you can really prompt engineer the model to behave as if it is like an agent that is forming conventions in interaction with people. But there's a lot of interesting discussion around whether prompting, like whether we want these models to a priori just like do this when we're interacting with them, or whether prompting is fine. So for example, this really nice work from Omar Shaikh at Stanford last year was looking at how LLMs that are not prompted to do like specifically these things perform what are called conversational grounding acts. So things like asking clarification questions, not assuming background knowledge, or not making assumptions about the conversation participants. And found that they really don't do this by default. Like, for example, if in this therapy case, someone says, I don't have close friends because I don't trust people, human response might be, you said you generally don't trust family or people in general, as a question. But maybe ChatGPT will say, I understand that feeling. Building trust with others can be challenging, particularly if you experienced past betrayals or disappointments, making this assumption that that's what the person has had experience with. And again, we see this like issue where the response is like very, very verbose, which is not very human-like, right? There's also this work from last year that hypothesizes that this as the default behavior is because these models are trained only on observations of single rollouts of conversations for people, rather than having these models learned by actually interacting with them in multiple turn interactions. And one of the examples they gave of this is in this sort of conversational drawing task where one person has something that they want to be drawn and is communicating to a drawer, right? There are different questions that a listener might ask to resolve different ambiguities. So, the person describes the scene, and then, one person asks which way is the owl and the cat looking, but someone else says tree hole facing which direction, or how big are cat and owl? People ask different things. And this is another example of how if you roll out in an interaction, you're going to get to very different places. And the ability for your model to participate in that, like going out to a very different place, is like one of the main challenges of these multi-agent systems, and not necessarily one that we're evaluating or getting these models to do. Another approach that, again, I believe Natasha is going to talk about in more in depth is multi-agent reinforcement learning, where we're actually training models to be good at modeling other agents in context through reinforcement learning. And there's a couple different ways that, two main ways of modeling these RL problems. One is a decentralized approach where every agent is trained independently of each other, maximizing its independent rewards, and the influence of other agents in the environment might not be explicitly modeled. So this is what this previous question was referring to, where you just have a policy and like other agents can change the environment, but you're not explicitly modeling what they're doing. You're just trying to maximize your own reward. Maybe it's in your best interest to model other agents, but you might not, like in practice, we might not do that. We might not have to do that. The other option is a centralized approach where we're training a single policy with its action space being sort of the cross product across all of the agents' action spaces. So you have 10 agents, each of them can move left, right, front, back. Now you have 10 different 10 times 4 actions that you could execute. Because you can choose the action for each of the sub-agents. And so that's sort of like architecturally how you might implement these systems, but how do you train them? Typically through what's called self-play, where you pair learning agents with copies of themselves in an environment, and then you perform rollouts by sampling from these policies and executing their actions, and then you collect rewards as you normally would in any sort of RL environment, and use them to update the agent policies. But the key thing here is that, and why it's called self-play, is that you're making copies of yourself and having interactions with copies of yourself, basically. And this doesn't necessarily include communication, so I wanted to highlight sort of a subset of this work referred to as emergent communication, where not only are we training these policies to take actions, but we're allowing them to have this shared protocol. And a lot of this work is coming from, I don't think a lot of people are working on this right now, but a lot of this work is coming from Angelica Lizardu at DeepMind in London, where, for example, in a reference game, again, we have a speaker, which is taking images and target and producing an utterance, and you have a listener who has images and an utterance is trying to pick something out. And the pair of agents is going to receive a reward based off of whether they pick the same thing, whether the listener grabs the same object. And so this has been like pretty well studied. You can train these agents, clearly, But I think one of the questions that is open here is like, are the learned communication protocols human interpretable? And how could we shape the learning process such that they are? So if you do this process and then you say, okay, what are the different words that the agents have like emerged as communication words? Like, are these things that like now you compare the agent with a human and perform well? And so there's a little bit of work on this as well. Another set of work, which is quite different than what I talked about previously, is like sort of explicitly representing other agents' beliefs and actions and so on through Bayesian theory of mind, where you have some explicit representation of their beliefs. So you have, you know, as you're doing the modeling problem, you have access to what's going on in the world and what is going on in your own internal state. But if there's another agent, you know, you want to model their belief and what their desire and goals are, and then you can also, you know, observe how their actions influence the state of the world. And so there's two sort of directions of this. One is, can we build an explicit model of other agents' beliefs, goals, and actions by observing their actions? And so, for example, this is a sort of a very simple example, and from some of this earlier work that proposes this, where you see this video of a little blue guy who is moving around in an environment. There's 3 different food trucks. There's, I don't know, Mexican food, Indian food, Chinese food, I don't know. So, or I guess Korean and, well, I don't know, it doesn't matter. So there's K, L, and like M of the food trucks. So the blue guy, you know, goes here, goes up a little bit in frame 10, and then goes back down. So which of these, so we know that K and L was here. Which food truck does the blue guy like? Any answers? Okay. Well, he likes, so what's the order of there's 3 different possible food trucks. K, L, and M. Which one does the blue guy like the best? If K was number 1, why wouldn't the blue guy just go to K originally? Yeah, so, okay. So, you know, maybe it takes some thought, or I don't know. Maybe I'm not I think probably I'm not presenting it very well, but the rationalization is like K, like this little blue guy likes M food truck the best, which is not actually in this environment at all. And the reason that the reason that the blue guy, you know, goes up and then back down is that the blue starts by not knowing which food truck is at the top because it's in gray, it's not visible to the blue guy. And once the blue guy sees that hidden food truck is L, they're like, okay, I'd rather go to K than L because my ordering of preferred food trucks is M is best, K is second best, and L is my least favorite. So by observing this, we can build a theory of like what are the beliefs and like and desires of this little blue guy, right? And not only that, we can perform explicit inverse planning over these models that we build to communicate, to act as if we are communicating. So one example that I really liked from a paper a couple years ago at SIGGRAPH was this acting as inverse planning paper from Kartik Chandra, where, you know, we want to animate a scene that demonstrates what the sort of underlying belief states are of the actors in the scene. So let's say the baby wants the cupcake and not the candy. And the fastest point to the cupcake would be to go straight through these black boxes. But a viewer would not be able to understand, or it would be harder for the viewer to recognize that that's what the baby was trying to get to, because it's ambiguous. Like that looks like the baby's going for the candy, right? So instead, it might be pragmatic for the animator to make the baby go around to get the cupcake, even though it's a less efficient path, because that's going to make it easier for the viewer to rationalize what the beliefs of the baby are, or what the goals of the baby are. Okay. And if you're interested in this, a lot of this work is coming from Josh Tenenbaum's group at MIT. There's a lot of cool variations of it. Okay, any questions about modeling agents in multi-agent systems? Yes. Mm. Yeah, I mean, so the question is more about like, how do you get people to understand the rules and incentives a priori, right? Yeah, I think it's a really good question. And it's something that people think about when designing these games and tasks. And so a lot of, I talked about the melting pot set of games were influenced by like theories of economics, but actually even there, like you kind of have to know what the incentives are a priori. So this becomes more of like I guess a communication channel. Like how can you or maybe like a game design problem where like it has to be clear to all the players like what the incentives are. In my own anecdotal experience, a lot of that is just iterating on the instructions we give people. Or doing trial periods where we're like, okay, here's a reward. Here, like let's play the game to start with. I mean, this is also just very common in like board games, for example. Like if you're trying to play a new board game, you'll do like a little trial round first to understand the dynamics, and then you go into actually playing it. So yeah, that's a great question. Cool. Okay, I have a couple minutes left, so I'm gonna just briefly go over why do we actually care about this? Like, what are the applications of this, and what are people doing with multi-agent systems right now? Okay, so one of the like biggest things is humans are going to be collaborating with these systems, right? And that's a multi-agent system. As soon as you have a person and then a system like a machine in the system, like people are going to form beliefs about these things. These things should also form beliefs about us, right? And so this is like a really important and almost like very clearly like obvious application of multi-agent systems and studying how multi-agent dynamics evolve. And some of the like more direct applications of this, for example, it would be like a lot of this work on legibility. So for example, coming from like Anka Jargon, where agents should take actions that are not only like executing their goals that they might have, but are legible to human users. So this little illustration is showing that, if the robot hand wants to grab the green ball, the fastest goal to get there, or the fastest way to get there is to just turn and then go, right? But if it's right next to this red ball, maybe it's more informative to a user if the robot hand avoids the red ball as it's moving and goes to the green ball from like the opposite direction, so that it's maximally informative as it is acting what its goal is. So this is like legibility. And also on the top, there's this, handwriting is another example. Like if like I know what the actions are that I should take to write this out, then you're gonna have like a really messy handwriting. But if you want to write it to be legible, then you should like maybe take more time. And in general, like agents should be modeling and accommodating their users. So there's this position piece from Katie Collins and other people at MIT, looking at how like if we believe that people are thinking about each other when we're interacting with each other, then we should be also having models model their machines modeling their human users, so that they are most accommodating to them. Another application of these multi-agent systems is like task decomposition and distribution. And so you might have seen a lot of this like LLM, agents, like multi-agent things where you compose a bunch of different agents that are prompted in different ways as like a system to execute a single goal. One example of this would be like the multi-agent research system from Anthropic, where you have a lead agent that like tells all the sub-agents what to do. And you have different agents that are responsible for different tasks, like searching for different things or finding citations or whatever. And one of the benefits of this is to break up tasks, difficult tasks, into smaller subtasks, where you can have specialized agents that are better, like best prompted for like a particular subtask. You can have these agents specialize. You can have them communicate with each other. And then we have some other recent work that is sort of piloting like this ability for agents to sort of dynamically delegate tasks to themselves, which supports like parallelization of task execution, which means that we have more efficient inference. And also, like instead of having a single agent that is keeping track of the entire rollout in a really complex task where you really are pushing up against context window limits, if you just break up the task, you have much smaller contexts for each of the subagents. There's a lot of recent work that is proposing to use these multi-agent systems to gain insights into social systems, like how people might behave in like multi-agent games or in different social scenarios. So a couple different ways that people are doing this are they are like trying to model individual people and like personas based off of like interviews with people. Maybe we can model their interactions. Maybe we can make conclusions about how policies like might influence like human behavior. I am like pretty like skeptical of a lot of this work because I think that human interaction and social interaction is like much more complex than whatever we can get out of an LLM. And there's also this big caveat, which is that LLMs and other machine learning systems are necessarily going to flatten these groups and replicate stereotypes. We know that they can't model long tail situations. So, there's empirical and theoretical, like empirical evidence and theoretical, model like theoretical arguments as to why like this is not going to give us like the best, like this is not going to be true to life, and therefore we should be really careful about this. And then the last thing I want to talk about is using these multi-agent systems as a way to actually improve individual agents themselves. So one example of this that I liked that's recent is coming from Jacob Eisenstein and a couple other people at Google DeepMind, where they designed this game to train models to be better at calibrating their confidence linguistically when answering questions. The high-level question here is, we know interaction design influences language use, so can we design games that elicit certain kinds of language use and learn through self-play? So in this work from DeepMind, they are doing collaborative self-play for linguistic confidence calibration, and they propose this game with 3 agents. Agent A has no tools. It just is asking questions of the other agents. It needs help from B and C, who do have access to the tools. And agent A will, B and C will go try to answer the question, come back to A with an answer, and then A is going to choose the answer of the one that sounds most confident. One of the 2 agents, for example, agent B, has a search tool that is useful, or actually in this case is not useful. It's like incorrect. But the other agent has a search tool that would give you the answer. And through the self-play, what could emerge from this, and what empirically does emerge from this, is that agents learn to hedge in their responses. So by saying things like, well, I think the answer might be this, instead of the answer is this, based off the information they get from their tool use. So in order to win at this game, you want the agent that doesn't have the full information to hedge linguistically, and you want the one that does have the full information to be very confident. And so that's what emerges from this training process. And then finally, we have, there's a lot of work recently, including from my own group and you have Artsy's group and a couple other people on learning to interact through interactions with human users, where the general paradigm is we deploy agents in interactions with human users. We observe the user's behavior. For example, the communicative success of an agent that is, in this case, generating instructions. So the agent generates some instructions, the human acts in response to those instructions, and then we can learn from this. This gives us a learning signal. And we can see over time, just by having a human follow natural language instructions generated by an LLM, or I guess this was a transformer model, we can improve we can improve task performance. The model gets better at describing what it wants a human to do. Okay. All right, so just very briefly, we talked about what is multi-agent systems and what it requires us to model, including other agents' beliefs, desires, and intentions. We talked about different game environments and how we can use interaction design to elicit different kinds of behavior. We talked about how we might train or implement these models through, for example, multi-agent reinforcement learning or through explicit modeling of other minds. And then finally, we talked about some of the reasons that people are looking at this problem, including that we want systems that can collaborate with us, and then we can use these systems to learn to improve agent performance through interaction. Also, this is the current Berkeley NLP group with some people who have graduated, and then a number of people who were not in the photo who have come in recently. And I also wanted to thank Nick Tomlin and Dan Fried for some feedback on the talk. So thank you.